Hey, it's Peter here with my FSHD. All right, we're back with kind of part two of our giant podcast on the Epicrispr EPI-321 gene therapy trial. And the first part, we went through I just want to make sure to get everyone up to speed on the background and the general concept behind the technology of CRISPR inhibition and the different types of CRISPR inhibition. But now we're going to really we're going to get into trouble now, right? Because we're going to look at the publicly available data. Now, we're putting ourselves out there, right? Chris is going to join me, and, I got to tell you, we were advised against doing this. Said, it's just sort of like unprecedented, really bad idea. It's going to bite you in the backside, And I think, why? Well, look at the data. This is actually what I do. This is the job of being a scientist, right? You present your own data, you critically evaluate your data, you critically evaluate each other's data. Peer review data goes back and forth. As long as you're not working on COVID vaccines, you're allowed to criticize people's data and raise concerns and try to validate it, right? And so if your data should stand up to scrutiny. In fact, that's what a publication is supposed to be. Right? You've put together your data set, you have a hypothesis, you test it, you do all your experiments, get all your data, then you send it off to the competition. And then the competition looks at it and they say, well, I don't really buy this, or this wasn't done quite right, or this should be done differently. And a whole list, you get pages of comments. And you respond to the comments. Say, well, okay, well, we disagree with you here. It's fine to disagree on some parts, but there, in the end, though, there is an answer with science. And you may disagree on the impact of the answer potentially, and sometimes it's valid, sometimes it's not. Right? We're just evaluating the data. Does it support the hypothesis? Was the experiment done right? In fact, that's always my biggest thing when I teach is, what's the question? Design an experiment to answer the question, and design the best experiment to answer the question. And if doing the experiment won't answer the question, what's the point in doing it? It's because, the experiment worked, did it not work? Well, if the experiment was designed correctly with the proper controls, and the system is set up to test what you want to test, and the answer is, well, it's always the right answer. It might not be the one you want, but is it the answer you want? Is it the correct answer? There is a right answer in science. Okay, you can like it and dislike it. I can support you or not support you, but you get an answer. Okay. And there are caveats to systems, and people do game the system sometimes and design experiments to give an answer they want. That's very dangerous. Oh boy, it does happen. It happens all the time. And won't guess the motivations when people do that. So sometimes they're just too damn dumb to design the right experiment. Sometimes they don't know any better. But honestly, I'm well aware sometimes when people purposefully are designing experiments to get that. You can just tell, right? But that doesn't matter here. The data's been done, the experiments have been designed. We're going to go through it in detail, put ourselves out there, and we do understand that we are going to get hammered online. Just ask them, do you disagree with the science and our evaluation of the science? That's all it's about, nothing personal. It's about the science. Do you have a different interpretation of the science? Does someone else have a different interpretation of the science? Can you find another researcher out there who will put their name on a different interpretation? Fine. Debating science is fun. Love it, because you know what? I'm more, if someone can convince me that I don't know what I'm talking about, that's fine too. We are here to get the right answer for you, because you deserve it. Okay? And so why are we doing this? We are opening ourselves up to a lot of criticism and who knows what. Well, because someone has to advocate for you, right? This is not a game, all right? Getting involved in any clinical trial. You deserve to know and understand, have the opportunity to understand the science behind it, okay? Evaluate it for yourself. I know you're not scientists, so that's why we're here. And you're more than welcome to get a second opinion, always, all right? But remember, no one else is putting themselves out there. Doesn't appear that anyone else is on your side, right? We're not out there just saying something's good or bad just for the hell of it, right? If the science is good, I'll tell you it's good. If I think it's a good trial, I'll tell you it's a good trial. If the science is bad, I'll tell you it's bad. If I wouldn't recommend a trial, I'll tell you I don't recommend the trial. I'll tell you why. Okay? I want you to understand why. I'm willing to put my scientific professional reputation on the line because that's what you deserve. All right? I'll take the heat because you're taking the therapeutic, you're taking the clinical trial, you're doing your part. The least we can do as a community, scientists and industry, is make damn sure we're giving you something that's got a chance, was developed appropriately, was tested appropriately, and that everything that could be done ahead of time was done before sticking it in you. You're not the experimental animal. You're the final piece of the puzzle. We're not running experiments in you that should have been run in other systems. At least I'm not. That's just me. All right. All right. Come on, Chris, let's get back going. All right, so here's part 2. We're going to look at the Epicrispr publicly available preclinical data. So what are we doing? I'm just going to make sure that it's absolutely clear to everybody, right?
Yeah.
Call this covering your ass.
For whatever good it'll do.
Whatever good it will do. That we're going to present our scientific interpretations of the publicly available data from Epicrispr Biotechnologies, from their website that they've shown at meetings. We're going to integrate their data with what is known in the neuromuscular disease gene therapy field, including preclinical data for other gene therapies and prior and current neuromuscular disease clinical trials to inform our opinions on the potential impact of the presented trial design on FSHD patients. So in some ways, it's kind of a two-part thing. One, we're going to evaluate the data that they've presented, that is presumably the foundational data of their approach. That is, they've used that data to then formulate this clinical trial. And, we will give our opinion and interpretation on the potential for benefit to participants in the trial, right?
Yeah.
We do not know, but with the vast wealth of data out there, you can make some pretty good estimations. Right?
Yep.
All right, so go to their website if you want to, Epicrispr Biotechnologies. They used to be called Epic Bio. The future of genetic medicine. Use the highly specific targeting feature of CRISPR to regulate and modulate gene expression. They're a platform company. It's actually a cool company. Actually, I think the technology is cool, right? I mean, what they're gonna do is they're gonna use very small, novel Cas proteins that they've designed. So the way they're gonna fit everything in is to make a super small Cas.
Yeah.
And then
Which is great because Cas is by far, when we show you pictures of these things, schemes, they are totally not to scale. You have to remember that the Cas protein is huge. It is taking up the vast majority of space in these things. All the other important components are really tiny compared to the monstrous Cas.
So from a company standpoint, just ignoring the FSHD part,
great platform.
I think it's a cool platform.
Yeah.
I actually love it. Right? It's going to call it the GEMS platform. Don't remember what it stands for, but the idea is that they have it's all focused on this DCas onyx, this ultra compact Cas protein, dead Cas. They can fuse any activity they want as long as it still fits, right? Turn something on, turn something off, affect potentially splicing. So this has applications to a lot of diseases beyond FSHD.
A lot of versatility.
It's a platform technology. Right. Okay. So just happens the first one they're using. So we're not knocking the technology at all. And the modulation they're going to add is repression by DNA methylation, DNA methyltransferase. They have a muscle-specific promoter, which if this is to scale, is striking.
No, it's just the words that take up a lot of space.
Okay, that probably must be what it is. And then they have the guide RNA. So you have the guide RNA, your muscle-specific promoter. So the guide RNA is going to tell the DCas where to go to methylate, which is going to be the D4Z4.
Yep.
What do they say about it? Well, again, I'm doing all the talk, but this is what their company says. So here's Alexandra Collin de la Horte, PhD, Vice President of Therapeutics at Epicrispr. And what she says about a year ago is the key takeaway is, this is at the American Society for Gene and Cell Therapy, the The key takeaway is that we can rescue methylation on that particular locus in the genome, and that correlates very well, and that translates very well into a suppression of the toxic gene target that is the cause of that disease, a complete reduction of cell death or apoptosis, and eventually a rescue of muscle function. Sounds great, doesn't it? Those are the key takeaways from the product that starts with the root cause, the methylation, and all of the positive effect that restoring methylation has on that disease. Okay, so what I get out of that is what they're saying is based on their data. She's saying their data says that they completely eliminate, they said complete reduction. A complete reduction is elimination of cell death or apoptosis, which is not something people typically look at, but whatever. Okay. They rescue muscle function, so that's pretty striking. In the end, functional rescue is the most important thing, so I'll be curious how they do that. And that they rescue methylation. And to me, rescuing methylation means you go from FSHD level of methylation to a non-FSHD level of methylation.
Asymptomatic.
Not just changing a little, but rescue. It's a rescue.
Sure.
It's flooding. They don't just put you up on a couple of steps. They take you out of the they take you out of the river.
Remediate.
So that's pretty strong statements. Okay. Hope it's true. Because again, we will evaluate the data. That is their interpretation. That is what they say their data says. Okay, and we're just, again, scientists can disagree, and scientists can also agree. More than I hope we agree. All right, it's another thing. There's a lot of stuff out there. These are just some of the things I picked because I want to give them a chance in their words, right? So this is Epic Bio's big swing in epigenetic editing from July 11, 2025, the business of biotech, right? Engaging with the FDA for a new drug modality requires a bold, evidence-based approach. Saltzman is Amber Saltzman, who is the CEO of Epicrispr Biotechnologies, right? Mm-hmm. Saltzman advises biotechs to follow the data, follow the science, and advocate for scientifically sound results. And I could not agree more with that statement. That is a absolutely correct statement, right? Follow the data, follow the science, and demand, not just advocate for scientifically sound results. We really hope we get science. Demand science. I demand that from you guys. I don't have a problem because you guys demand it from yourselves. Well, seriously, you never have tried to. You have never come to me with something where I've said, and tried to sell me something that's not really true.
What would be the point?
What's the point? Because the whole point is to get the right answer.
Yeah, of course.
Say, this is what the experiment I did. This is what I got. What do we get?
Good scientists do exactly this.
That's what scientists do. For FSHD, this goes on. This is written by Ben Comer, chief editor for the Life Sciences, by the way, of the business of biotech. For FSHD, Epic Bio proposed using methylation data as a biomarker, since increased methylation correlates with reduced disease severity. We showed that, of course, yes. That's actually work a number of labs have shown. While the FDA agreed with the correlation, they encouraged human studies to prove that changing methylation directly alters the course of disease. So, Saltzman is optimistic regarding the current FDA and praised Commissioner Martin McCarthy's constructive ideas for streamlining submissions and embracing innovative tools like AI. We have our own opinions on AI. We're not going to show any AI data. I know that they did some AI work, but we're going to leave that alone. All right, and then finally, this was one last interview. Actually, I listened to the whole podcast here from Amber Saltzman, 26-minute podcast. We're not going to show her already long enough. But this is called Rare Daily and Global Genes, using CRISPR to modulate gene expression. This is May 29th, 2025. And it's called the Rarecast, and I would recommend listening to it. Epicrispr Biotechnology is using CRISPR to modulate the expression of disease-causing genes without making cuts to DNA. So a little bit about the overall platform technology. Its lead program is in development to treat FSHD. And we spoke with Amber Saltzman, CEO of Epicrispr, about how this one-and-done therapies target the epigenome. And, she spent a lot of time talking about their personal interest in FSHD, of having it been in the family, and how much they care about patients, and why they're using AAVrh74, and for safety. And so there's a whole lot of reasons for things in there. So it's worth listening to, because you kind of hear it from them. I don't try to guess what's in people's minds, right? We can evaluate the data and say, this is how you evaluate, this is how we evaluate. I don't know people's motivation, so I let them speak for themselves, and I think that's appropriate. All right, one of the things though that's cool, because RH74, AAV-RH74, if you listen to our previous podcast, you're going to hear that it's not a very good vector. On one hand, it has been in many people, many neuromuscular disease patients, and has generally a good safety profile with a few deaths. In fact, it was so good from a safety standpoint, so predictable from a dosing standpoint, that it received what's called platform technology designation by the FDA. Okay, and this was Sarepta. Sarepta is kind of the main purveyor of RH74. It's an old vector, one of the kind of original natural serotypes, and it's cheap. No licensing really for RH74, if that's an issue for anybody. But you need to use very high doses, and most of it goes to the liver. And Sarepta has done this in enough patients that they can figure out what's the upper limit on a kind of safe dose that has debatable efficacy in Duchenne muscular dystrophy, right? But since there have been so many patients, Amber says that was the selling point for them on AAV74. They don't mind that you need to use a ton of it, and they don't mind that the deaths are rare, and they don't seem to mind that most of it goes to liver. The key is that you have all this data out there, patient data, that you can rely on, so you can get your dosing, your biodistribution, your cargo expression. It's just, there's probably more data on RH74 than any other virus out there for neuromuscular disease gene therapy in people. So that's why they're using it. However, a month later, FDA revoked platform technology from RH74 because of several deaths. In fact, they decided that evidence is insufficient to demonstrate that the platform technology has the potential to be incorporated in or utilized by more than one drug without an adverse effect on safety. So now the FDA, after a few deaths from the high dose RH74, and again, you need to have these high doses, 10 to the 14th viral genomes per kilogram, to have any efficacy.
Any hope of efficacy. Yeah.
Right, and Duchenne, right, you decrease that,
Yep.
and you don't get efficacy in Duchenne muscular dystrophy. Right, so you need to have these high doses, and that can be some problem because it's not a very good virus. All right, so let's look at some data here. All right, so again, all this data came from publicly presented posters and downloaded from the Epicrispr.com website.
Yep.
Right. Okay, so what's this say? This says EPI-321 represses DUX4 and rescues apoptosis in 6 FSHD patient-derived primary myoblasts. Okay, now one of the first things, they always talk about primary myoblasts. And if you actually take them at their word on how they do these experiments, they're always working on myoblasts, which are replicating cells. They are treating replicating cells on day 0, myoblasts, and then differentiating them over 6 days. Okay, so the thing to keep in mind is your skeletal muscle is not replicating. Okay, so they are choosing an idealized system to do this. Okay, replicating myoblasts for infection and establishment of methylation and repression. This is an idealized system. Okay, not clinically relevant. Okay, so in this idealized system, now again, remember, we're just reviewing the data, and my interpretation of this is that it's an idealized system.
Okay. Replicating muscle cells, proliferating myoblasts in culture. If that's what's being treated, that is not
that is what they are doing, and that is not the target tissue in FSHD. Right. And in my opinion, this is not testing the therapeutic in a clinically relevant manner.
Now you could say, well, why does it matter? And there may be cases where it doesn't matter. The reason it matters in this case is because what they're attempting to do is target a DNA methyltransferase to the FSHD locus. And they need to show that they can do that in the actual target tissue.
So what they should be doing is differentiate for 2 or 3 or 4 days.
Yeah.
Then infect.
Yeah, because the question is, can differentiated skeletal muscle fibers actually change their methylation?
Without replication.
And the reason that's a question is because it's never been shown. It has never been shown.
So you could conceptually say, well, you're recruiting the methylation machinery to a non-replicative locus.
Right.
You could conceptually see how that could methylate a piece of DNA that's there, or a CPG that's there, but we weren't able to do it.
Yeah.
Which is fine. We can't do everything.
We assume other people have also tried.
We've not seen, nobody in the literature has ever shown that. And
That's
going
right.
through all their
the one bioarchives paper we showed you from Sasaki Honda was done in iPSCs. That was where they treated.
So nobody has been able to
and then
show
differentiated to muscle. So nobody's actually shown, in this quiescent differentiated skeletal muscle, the target tissue for FSHD, can you change methylation at D4Z4? That has not been shown, which is why we're hammering this point.
Yeah, because it's very important. But so idealized system, replicating myoblasts, easier to establish. What do they get? So first thing here in panel B is viral genomes per diploid genome. So how many virus particles basically got into the cell, okay? And I'm going to say about 12 is on average about 12 plus or minus 6 or something.
Which is not bad compared to,
this is in
you
vitro.
did these numbers, you ran these numbers through, I think, on your other podcast, right?
Yeah.
In terms of effective gene therapies for
12's the
dystrophin
ballpark,
expression,
yeah.
For getting
12's
functional
great.
rescue in Duchenne models. So 12 is pretty good. Okay.
So they're getting 12 in. We don't know what the dose is, but they're getting 12 in. And if you get 12 in, you make a ton of transcript. Makes sense, of course. Control is
nothing.
Fine, right?
Yeah.
So you make a ton of the cargo, and you get about a 40% reduction of DUX4.
Which is very believable. That's
about
what we see, 40,
believable.
50, 40 to 60% reduction. Yeah.
It's hard to get DUX4 down to 0.
Very
right?
hard. Yep.
So if you get 12 copies of the thing into probably almost every cell, 12 copies of EPI-321, you get about a 40% reduction in DUX4 mRNA. Okay. Then you also get a 30% reduction of apoptosis. That was my math down here. I'm looking over here at panel D. If you're looking online, caspase-7, which is a marker of programmed cell death. They tend to cells that are going to kill themselves express caspase-3, and it's going to lead to cell death, and caspase-7. And so they're going to measure this, and they're going to see. I count this to be about a 30% reduction. It's hard to see the scale there. That's 6, there's 4, there's 2. It's not a log scale. And okay. So remember, they had told us it was a complete reduction of apoptosis and suppression of
right.
Okay, so not quite living up to standard. But again, they're reducing, we can basically say 12 copies per cell, 40% reduction on average of DUX4, 30% reduction of apoptosis. At least that's my take on it. All right. So now this actually matters. We're going to kind of jump ahead a little bit, and this is where we're going to integrate. Remember, FSHD is so fortunate because we have all this data from other neuromuscular diseases that have been doing gene therapy for years, right? So you don't have to start from scratch. You basically can say what has worked for others in the past, what has worked in animal models, what has translated to the clinic, and actually there's a ton of it for AAV-RH74. So as Amber said, that's, they're using it because there's a ton of data. So let's make sure we use the data. We seem to be aware of it. Okay, so if we go to this paper that we had studied, basically in the previous podcasts, right? This is the Sarepta data for the Elvidis trial in the mice, dose escalation study of systematically delivered RAVRH74, microdystrophin, and the MDX mouse model of DMD, right? What can we learn? Okay. So there's a bunch of data on systemic delivery and biodistribution to the muscles using AAV74. Okay. And so we know from the Epicrispr data that about 12 genomes per nucleus gives you a 40% reduction. Okay. The Epicrispr trial, we'll jump ahead, is going to use 2 times 10 to the 13th vector. Sorry, Brad. Brad, my angry, Brad, he didn't like the numbers from the previous. He's like, oh my God, these numbers.
A lot of numbers in science.
A lot of numbers. I know. He can calculate WAR and batting average and pitch count. He can do all the baseball stats, but he didn't like these viral numbers. No. Sorry, Brad. All right, so Epicrispr is going to use low dose 2 times 10 to the 13th vector genomes per kg and a high dose of 4 times 10 to the 13th vector genomes per kg. This is their clinical trial dosing in participants in the trial. Yeah. Okay, so if you kind of work your way back and you go to what can we learn from the DMD trials in mice? And you say, okay, if we need 12 vector genomes per nucleus of RH74 in order to get 40% reduction, of DUX4 that they see, basically the target is 12 vector genomes. And you go to their data, basically what you need, right? You need a dose of 2 times 10 to the 6th vector genomes per microgram. So basically 14 vector genomes per nucleus. You get that from 2 times 10 to the 14th vector genomes per kg. Okay, that's what you need. You need to have a higher dose.
So 10 times higher than their lowest dose that's going to be used in the trial.
So if you just do the comparison with the DMD, so DMD, same virus, different cargo, and cargo does make a difference to some degree.
Sure.
Not a huge difference, but it does make a difference more on packaging, right, and potentially on expression levels. But if you just know, if you say, but actually that doesn't matter.
This is just a rough calculation, rough estimates based on other data, but...
But the packaging is irrelevant. Cargo affects packaging. That doesn't matter here.
Yep.
And cargo can affect expression level. Different cargos can be at a different level. But what we know is their cargo needs to be 12 vector genomes per nucleus
to see this level of
to get a 40% reduction.
Right.
And in order to get 12 vector genomes per nucleus, based on RH74 systemic treatment in mice, you need to be greater than 2 times 10 to the 14th vector genomes per kg.
Which they are not going to in their trial.
Which is 10 times greater and is actually higher than the safe dose for AAV RH74.
Thank God they're not doing that.
In fact, that was our initial concern when we saw our trials. We thought they were going to do that. Okay. So they're tenfold lower than we would expect them based on their own data to need.
For efficacy.
Okay, what can we learn from dogs? That's a mouse, right? Dogs, there's some data in dogs. Now, granted, the dog data this is going to be AV9, right?
Yep.
So AV9, so we changed it a little bit, but AV9 and RH74 are very similar in their dosing and their biodistribution. So if we're in a dog with AV9, what do we need to get to 12 vector genomes per nucleus? And again, the dog data, if you're looking at vastus lataris, biceps femoris, cranial sartorius,
all anatomical muscles, skeletal muscles.
All anatomical muscles, you need to hit this. Basically, you need to get more than 2 times 10 to the 14th vector genomes per kg to get 12 vector genomes per nucleus.
So it basically tells us the same thing.
Right, 2 times 10 to the 6th, right? This is vector genome copies of DNA, right? 2 times 10 to the 6th vector genome copies per microgram of DNA in a dog is 14.
Yep, so even with the different vector, you still
if we just drop it down to 1 times 10 to the 6th, right? To get this, in order to get, vector genomes, right? You need 2 times 10 to the 14th vector genomes per kilogram.
Yeah, very high dose.
So you need a very, very high dose in order to get this, higher than that. Okay. So how did I get to those calculations? And is this actually, we can look in the previous podcast and go to it. But remember, the key is calculating vector genomes per cell or vector genomes per nucleus, because you have multinucleated cells, and it actually is an overestimate of how things are going in muscle and tissue. Now in cell culture in the lab, the idealized situation in the lab, you have one cell type
laid out flat on a plate. Every cell has equal access to whatever you're putting on it.
there's a pretty good chance that all 12 vector genome got into the nucleus and didn't get stuck up in the garbage.
Yep, it's a nice, easy system to use.
Right. In a tissue, like muscle, a lot of that vector does not get to the nucleus and never ends up getting expressed. And we have learned this when we deal with gene therapy companies, that a lot of times they don't even care about your vector genomes per amount of DNA or per cell.
We can tell you about anything about what's
You really want to look at the expression
of your transgene.
of the cargo,
Yep.
because that's what counts, right?
Yep.
Fortunately, the mouse and dog data did that. So let's look at the dog data using AAV9. Again, very similar, but not the same as RH74. Okay, 1 times 10 to the 13 vector genomes per kilogram, right? Which basically works out to be 0.2 vector genomes per nucleus. 1 vector genome per every 5 myonuclei, right? Only 5% of the myofibers were positive. Okay?
Yeah.
So 5%. And if 1 out of 5 myonucleus, basically probably, but only 1 out of 20 is expressing the cargo. All right, not great.
Nope.
All right, so go to the mid dose, 1 times 10 to the 14th. Now this again is 5 times higher than the low dose that's being used.
Now we're getting somewhere in terms of dystrophin expression.
Now you're getting 70% of the myofibers are positive, and they're expressing about 15 to 30% of the wild type levels, right?
Yep.
And so you're getting around 70% positive. So this is 7 vector genomes per nucleus if you're going to do that calculation. Again, it's an ideal calculation. Now, in an ideal world, they need to have 13 or 12, whatever we worked it out to be, vector genomes per nucleus in an ideal situation. Here's a less than ideal situation, but more biologically relevant, right? Okay, so a dose 5 times higher than the low dose, or 2.5 times higher than the high dose,
Right.
actually is kind of, now you're getting somewhere.
Yeah, and that's basically the bottom, the lower threshold of efficacy, right?
Right, and you're still within a safe range,
Right.
1 times 10 to the 14. Okay, so concerns about, are they going to get enough vector genomes into the muscle cells to get their 40% reduction of DUX4 and their 30% reduction of apoptosis?
Yeah.
Okay, all right, let's go to another figure here. EPI-321 rescues D4Z4 epigenome through DNA remethylation in FSHD patient-derived primary myoblasts. Presumably they're doing the same thing where they treat cycling cells, then they stimulate differentiation after the virus gets in, and then they establish methylation while the cells are differentiating, right? So to speak,
Yeah.
or whatever.
Yeah.
Okay, and so what they get, now I gotta tell you, I've spent the past 30 years studying DNA methylation.
Yeah. We know. Still are.
29 years.
Yeah.
All right.
You know a little bit about
I
it.
know a little bit about it, and I've spent the past 20 years
Specifically
on
FSHD.
FSHD DNA methylation.
Maybe the most complicated of all.
And I've never seen DNA methylation data presented this way. And this to me is absolutely uninterpretable. I honestly don't get it. If you're looking online, we're in panel A, percent methylation, control,
Treated.
says a control test article treated. I don't know if that is now non-targeting guide. That would be the right control. It would be a non-targeting guide. Don't know what the actual control is. But EPI-321, they say they get an 8.5% increase in methylation.
Yep.
Most FSHD patients are further than 8.5% methylation away from
From an asymptomatic
asymptomatic
level.
or healthy.
Yeah.
You may be dialing it back.
Yeah.
Now, I don't know what this actually means, so I'll be careful. I honestly don't know what this means. I don't know if it's like one little band here
know. I don't
gets
know what each of those
methylated
lines
really
are.
well and none of the others do, and that'd be even worse.
Yeah.
I mean, presumably, well, honestly, I got no idea. It's uninterpretable.
It's almost like each line is a different methylation level, and the width of the
Well-
line is the number of
I got no idea.
chromosomes.
No, I have no idea how to interpret this data.
Yeah.
But we'll take them
Okay.
for their word.
We'll keep
An
going.
8.5%.
Increase.
I mean, if you're going to make up data, you make up a better number than that.
guess
So I
so.
believe them.
Probably believable.
I believe that they're getting an 8.5, however they calculate it, because if you're doing everything in your power, when you present data like this, you're doing everything in your power to make sure nobody can understand it. And also make it the best case scenario.
Yeah.
What I'd like to see is the plots that I showed
Yeah,
previously. Actual methylation across the D4Z4 pathogenic locus of the distal repeat unit. That's where it matters. I actually don't even know where this methylation is.
No, we don't know.
No, I'm sure they.
A lot of information.
I mean,
not
so
here.
I don't know if this is the distal repeat, all the repeats. I got no idea.
Yeah.
It could be that it's 8.5% because all the other ones are methyl. I don't know.
Yeah.
But then you're looking at this methylation. Sorry, I mean, we just better stop.
Yeah.
I cannot interpret this at all. Now, it's funny because what they could come back to is we did publish a paper that showed the difference in siblings between a symptomatic and an asymptomatic sibling could be sometimes in that range. We saw some were like 6%, some were 12%. We know that some are even 20% difference. So dialing it back is good.
Yeah.
So with the right set of patients,
This might actually be.
this might be
be good.
beneficial,
Right.
potentially.
All right, so now I just want to get back to a point that Chris and I have both been making about DNA methylation and replication, and they're related, but also I want to address them a little bit individually, okay? Because there's so much focus here on, well, they say restoring, it says up here at the title, right? Rescues D4Z for epigenome through DNA remethylation in FSHD, patient-derived primary myeloblasts. Okay, so what does restoring the epigenome mean? Because they're asking DNA methylation, and if you saw if you looked at our previous episode, we went over this slide before. I'm going to go over it again, right? If you're looking online, right, which is really important, we got a cartoon of the D4Z4 distalmost repeat in the FSHD locus. On the right, in the FSHD state, where you have euchromatic epigenome, and on the left, a healthy non-FSHD state, where you have a heterochromatic epigenome. And that is true. There's lots of methylation in the non-FSHD, and virtually no methylation in the FSHD. Now, that's actually, I remember, the FSHD chromosomes aren't all 0% methylation. There's still some methylation there. Right, and there's a range of methylation. There's some that are 0%, but there's some up to 25% methylation, and there's still FSHD. So you can still have some methylation here. But for simplicity's sake, and this is simple, may not seem that way, this is what we got. So what Epicrispr is trying to say is by adding a little bit of this methylation, a few 8.5%, a few dibs and dabs of methylation on this FSHD region on the right, that now suddenly it's going to look like this FSHD region on the left. It is now not FSHD. Forgetting or ignoring that the epigenome is this conglomeration of histone modifications, histone tails with repressive modifications, histone modifying proteins, cohesions, heterochromatin proteins like HP1, alpha and gamma, SMCHD1, you have ATP-dependent chromatin remodelers, histone deacetylases, polycomb proteins, small RNAs that are maintaining this. This is quite an impressive feat compared to FSHD, where you have different histone modifications. These histone tails have active marks, or at least not repressive marks. Okay, they can be acetylated at different methylation marks, protein methylation. You have ATP-dependent chromatin remodelers, different ones. You have trithorax complex, ASH1L. You have the DBET long non-coding RNA, CTCF. So you have things that affect 3D structure, setting up chromosome domains in the nucleus, right? And so the idea that they're trying to say is by adding a couple of methyl groups here on the right, that all of this activation, all this euchromatic, all of this region here, in the absence of replication,
It's all just going to go away. And you're going to assemble this repressive machinery here over on the left, on the locus, ignoring the fact that the whole point of epigenetic regulation is to prevent that from happening, right? If it was easy, it wouldn't be epigenetics. In fact, it's incredibly hard, right? And so, yes, they might be adding a little bit of methylation here. They may even be, it's not, even if the cells are replicating, I'm not clear, it's not totally clear in their system that was going to set up really repression. Okay, and they say, well, you see, they're seeing, their 40% repression or their 25%, whatever percent repression they're seeing. So they are seeing some repression, so they're getting something, but it's not clear that the repression they're seeing and the little bit of methylation that they're adding are not just coincidental, two things that are happening. And we'll get to that in a second, okay? Right? So what they're doing do, right? They're saying EPI-321, a little bit of methylation on the right, going to come over here to less, it's different state on the left. Now we've talked about this it as a dial, right? But again, the way I really think of it, because we see this when we do our DNA methylation assay for diagnostics or research test or whatever you want to call it, is that there's this everybody has a range of methylation and a range of epigenetic states. And when we talk about dialing it back, what I mean is you just, you want to take some of the intermediate states and turn them, you are trying to push everything from the right to the left here, right? But it's not clear that just methylation alone is going to do it, right? Or how much methylation you need before you start actually nucleating enough repressive factors, if you ever do, and if you can even do it. I used to think that, well, if you methylate enough, you're going to recruit methylbinding proteins and you'll just set this up. But we tried it out and it didn't really work. And then the more we thought about it, these aren't replicating cells, and all the systems where it works are replicating cells because of the replication fork and the polymerase is going through. Kind of give you an opportunity to maybe switch this if you can physically target something with DCAS. Right, so can this actually be accomplished? I'm not convinced that the data showing that it can be. A little bit of methylation they showed. I don't know. Honestly, I don't know what that 8.5% means. And I don't know if that's enough. But let's go back to a paper that actually was successful, right? I just told you that I don't know if it can be done. Now, remember, all that EPI-321 is a portion of DNA methyltransferase 3A, as I understand it. Not sure how big it is, not sure if there's any 3L in there or not. But Mitsuru Sasaki Honda in this really cool paper, this hit and run, what they did, now they're not restricted by AAV, right? They can put any size in they want. So these DNMT3, these DNA methyltransferases are very large. The DCAS is very large. And so since they're in cell culture, they can use lentivirus or they can use other systems. And so what they actually did is they used DCAS fused to CRAB. They used both techniques. They brought in a repressor and they brought in two DNA methyltransferases, DNMT3A and 3L, the full size things fused together. It's enormous, but it brings in the methyltransferase activity and the transcriptional repressor activity, because one thing we know is that DNMT3A and 3B, these things are actually transcriptional repressors in addition to being DNA methyltransferases, right? So to set this up, they can actually recruit heterochromatin protein 1, HP1 can come in, and so not only are they methylating, but they're also bringing repressive machinery with them. And on top of that, what's known, this is a great paper from Stephen Balin, it's from 2001, at Hopkins, but this guy, Michael Rountree, is a really great epigenetics guy. It's kind of our my postdoc competitor. We were at NIH, they were at Hopkins, and we're kind of working on the same things, frenemies a little bit. But when they looked at this, they're looking at how to establish repressive chromatin. And they're saying that DNMT3A and 3B may help to establish repressive chromatin in late S phase and then maintain this repressive heterochromatin throughout the cell cycle in a developmental or cell type specific manner. But the key is The establishment is late S phase, which is DNA replication, replicating cells. The problem is the muscle cells that are going bad in FSHD, where DUX4 is expressed, are here. They're your G0 cells. They're not replicating. Okay, they're terminally differentiated. And so basically you don't have, so what we know, where you can use DNA methylation to establish repression on the FSHD locus, you need to bring in fact, there are other papers out there that show when you're using DCAS and target DNA methyltransferases, it works infinitely better if you also target CRAB, which is a transcription repressor. You have to do both. Bring in the repressor to shut it off, and bring in the methyltransferases to methylate it and keep it off, and to help establish, and then you can start to nucleate repression, okay, on replicating cells. And then you can get it to go, and that's what they got to do. So it's a very different situation than what's going on with EPI-321. Okay, so that's what's going on. So now we get back to this, right? We're back here, and the answer question is, the title of their the figure, restoring the epigenome. Are they? Does it actually say that? What I saw is that they added a few methyl groups here. Right? There are ways to do this. Actually, Carice has published experiments showing you can look at the histone modifications and you can actually show whether or not you are changing the histone modifications there. Right? Well, it's pretty tough. And I'm not going to give away what she has shown. We're talking about Epicrispr. They haven't shown anything. Okay, as far as other than they can add 8.5% methylation, whatever that means. Right?
Yeah.
Okay, so the devil's in the detail. Let's look at DUX4. DUX4 goes down like 99%.
Now, why is it going down to 99?
I have no idea
when
why.
The last one was, a more
so
realistic
this time it's
amount.
going down like almost to zero.
Okay, this is after day 7 of differentiation. I don't remember what the
I got no
last
idea.
one was.
So now we're down at 0.
But yeah, suddenly DUX4 is absolutely.
But DUX4 target genes
But the targets aren't doing anything
are
significant.
actually not even down to 40%.
No.
They're only down 25%.
Yeah, this is very
Remember, DUX4 is a transcriptional activator. It activates many genes that are not normally expressed in muscle cells.
Yep, you
One way to
usually see
measure DUX4 activity is to look for the presence of genes that they activate that would not be present in a healthy cell.
Right. Usually knockdown of DUX4 correlates with a knockdown of DUX4 targets. And this one clearly doesn't.
So control must be FSHD cells. These are the target genes, and then the target genes are down, right?
Yeah,
So,
yeah.
okay,
And it must be a composite. Yeah, composite score.
yes,
So however
composite
many
score,
targets.
whatever. It's going down 25%.
Yeah.
And apoptosis is going down now like 60%. Now, I'm not fussed about the variability because we work in FSHD enough to know that culturing conditions affect a lot of things. You're really looking for trends.
Yeah, sure.
But I still haven't seen what they've kind of talked about in their...
And apoptosis is a strange phenotype.
I don't know
measure.
anyone that has
We don't see this
apoptosis.
with, primary FSHD muscle
Properly
cells.
grown cells that are grown, yeah.
Exactly. And this is a tough
We-
thing in this field. Very few people actually know how to properly
grow
grow
cells, yeah.
muscle cells. Anyway, you can't morphologically tell the difference between FSHD primary muscle cells in culture and healthy muscle cells in culture. And the people who've seen rare phenotypes, they're admittedly very, very rare and usually a result of culturing artifacts, in my opinion.
Well, passage of the cells, treatment of the cells, culturing, like you said, all these things make the difference, the growth factors that are present in the cells.
Yeah.
Sometimes what people say is, well, it doesn't matter if you screw the cells up, because if they're differentially screwed up in FSHD versus healthy, that shows something. And if they're differentially screwed up with your treatment versus non-treatment, that shows something. So you've affected something. May not be biologically relevant, but it shows that you've, whatever.
Yeah.
But whatever, they're looking at apoptosis. It is true, if you take a plasmid expressing DUX4 and you put it into a cell, it will cause apoptosis.
Yeah, sure. Overexpression phenotypes are always very different
Whatever,
from.
but I gotta tell you,
biological
the
phenotypes.
apoptosis that they saw, I'll tell you, when they showed the apoptosis back on the tunnel assays back, we never see
we
anything.
never see
We
that
never see
on-
anything.
on our
And
cells.
again, that's our cells under
Yep.
our culturing conditions, very different. We're not, we're just saying we see different things.
Yep.
Right. So it's a little hard to interpret. But we can go back to what their vice president of therapeutics said. And their vice president of therapeutics says they rescue methylation on the locus, and they 8% plus 8%. That, in my opinion,
Does not
does not
constitute a rescue.
You are increasing methylation on some part of the locus that we don't know. But to say that you have rescued methylation on the locus
It's hyperbole.
is not borne out by the data, in my opinion.
Yep, I agree.
Okay. Complete reduction of cell death or apoptosis. Again, the data showed one time a 30% reduction, this time a 60% reduction. While that is a reduction of apoptosis, it is not a complete reduction of cell death or apoptosis. So I would say the data does not support this.
And what about this rescue of muscle function?
Now they're going to say, and eventually a rescue of muscle function.
We have some
Well,
functional
let's
data?
see. So I'm expecting to see a mouse, a pig, something, right? What we see is 3D muscle bundles, okay? Now I gotta tell you, it is true you don't have to do work in a mouse and you don't have to do work in a pig. I believe that muscle in an animal versus muscle grown in purified conditions in a dish, even 3D, is different.
Yep.
But a lot of people are moving to 3D. Even some people we know very well are moving, right?
Yep.
So let's look at the data. So what they're going to do is they're going to get FSHD cells. They are going to do some sort of 3D casting. They're going to now they're actually doing the right experiment. They're going to differentiate the cells, right? They're going to do functional tests to show they actually have muscle. And then on day 7, they're going to add the virus. So this is actually
This is a better experiment.
the correct way conceptually to do the experiment. And then they're going to do functional tests over like 46 days.
Right.
All right. So what's the concern? Well, I got to tell you, I checked with some people I know who develop 3D muscle culture, actually even in FSHD. There's some experts out there you can check with, and showed this figure to them. And they said it is scientifically uninterpretable. We'll get to that in a second. And I agree with that. That's why I was asking.
Yeah.
But they brought up this issue that says one of the big problems in 3D culture is the virus can't get into
Yeah, how does it penetrate?
the cells.
There's no vasculature.
So in a body, it goes through the vasculature, the capillaries, and it perfuses
3D
through the
tissue is
muscle.
like a chunk of meat.
A 3D tissue would be if you take a steak
Yeah, and dump virus
and you
on
drop it into your
it. How much virus is going to get to the middle of your
tenderizer,
steak?
right? How eventually, right? Is it going to get in? Is
Yeah.
it going? Does it all get in? Does all this, salt maybe does, but virus going to?
Penetration is a big.
In fact,
question.
we were told that is actually one of the big problems is getting that actually you have to do the wrong experiment. You actually have to add your virus
As it's being assembled.
as it's being assembled in order to get it in.
Yeah, that's the only thing that makes sense. But
So,
this
so
explains
you
why
can't
they-
do the right experiment. So, okay, so that's just basically a technical concern, which again, I am not an expert on 3D culture. We spoke with an expert on 3D culture, and they said that is a problem with 3D
explains
culture.
why they didn't get a dose response.
So let's look at the data. Now remember, this is their data to show rescue of function.
Right.
Okay. So untransduced, so they're going to measure force, twitch force, and they're going to do tetanic force. Okay. So they're going to basically measure how, kind of how strong are the muscle fibers, right? And if you're looking online, you basically have these two posts here, and you can measure, you grow the muscle between the two posts, and you can actually cause them to contract. You can train them to contract, according to our friend, and then you can measure the force of that contraction, right? Okay. And so when they add 7.5 million viral particles, that's 10 to the 6th, to this teeny tiny, how many cells do you think?
I have no idea.
I meant to ask that. How many cells are in 3D culture? Do you think it's a million?
You can grow up to 6 or 7 million dense muscle cells on it's a 100 millimeter plate.
This is a
that's a
24.
12 well plate.
It's a it's 20,
yeah,
it's a
24
24
well
well plate, and then you're in here and you're kind of So I don't know. You're growing them in a flask. You're putting them in. I got
how three-dimensional they are.
I have no idea. So we have no idea.
We won't even guess.
Okay, we won't guess. But we do know they're putting 7.5 million viral particles in there, and they get an improvement, a stronger, better muscle. And then if you add 10 times more virus, it doesn't change.
Yeah.
And then if you add 100 times more virus,
Doesn't change.
it also doesn't change.
Yep.
So it actually doesn't matter how much virus you put on.
And that's a penetration
You get
issue, I'm sure.
I don't know, because there's no controls.
Well, that's true. There's no control.
So what they told us, it goes from 1 to 1.5. It's going maybe to 1.65. They're saying that this is a rescue. This is a rescue.
But we have no idea what normal, healthy muscle fibers look like.
What does a healthy fiber look like compared to this?
Yeah, it's not done.
The other thing that our colleague told us is that anytime you add anything to these 3D cells, you get a change. So adding it could be that any virus at all, actually, because the control here is untransduced.
Oh, that's a very good point.
So the proper control is a non-targeting guide. Basically, if you take the CRISPR machine and the guide RNA that says go to the D4Z4, the control that, in our opinion, should be used is you use a different sequence that does not target the D4Z4. In fact, it should not target anywhere in the genome. And this way, everything's the same. You're just saying targeted versus non-targeted, and what happens. This will let you know, is this an effect of just infecting with virus that somehow is causing a change in the structure or not? We don't know, okay? We don't know. Now they may have, this is a case of that data may all be there. They have, again, poster, you don't put everything. I would put it on my poster.
Oh yeah.
I sure as hell wouldn't let my student or someone from my lab present a poster like this. You would have healthy muscle. If the claim that you're trying to make is that you're functional rescue, not improvement,
we need to
rescue
where healthy levels are.
I want to see healthy muscle strength made the same way. I want to see transduced with a non-targeting vector, and then transduced with a targeting vector.
Which any reviewer would point out.
And I want to see a dose response.
If this was
any reviewer, we're just reviewing this as a we're not picking on them. We're not. This is how I'm reviewing the paper. I'm reviewing. This would be
if this had gone out for peer review.
We're just making a reviewer. I just reviewed some preclinical data for a company in a paper that was spectacular. In fact, I even wrote to the editor, and I said this preclinical data from this company should become and it wasn't our company. No company I had nothing to do with, or I wouldn't be allowed to review it. And I even wrote a special note to the editor, said this should become like the gold standard of preclinical data in the FSHD space. And really strongly supported it. I'm telling you, if the data's good, we're positive. If the data sucks, we're negative. It's got nothing to do with who it is or what they're doing. It's just, you want to have a, I was up at, someone was asking, I remember Anthony Sala. Anthony Sala is the CEO of Myracule. He has FSHD himself. I remember somebody asked him, he told me, he said, how do you get Peter to like you on the podcast? He said, well, we don't talk at all. We don't do anything. And I told him, the answer is because you can do good work and you have good data. So that's how you get me to like you on the podcast. Have good data. If you have good data, we love you. Your data sucks, well, we don't love you.
Doesn't matter how many cookies you send us.
It doesn't matter how many cookies, although we do like the Scotty.
Feel free to send cookies.
Feel free to send cookies. It's all about the data. The data's the data. Boy, you know what? Seinfeld should do a routine like that.
He should.
The data's the data.
Because it's such a buzzword to say we follow the science. Everybody follows the science.
Well, Amber mandates. She says her advice is advocate for strong science.
It's become a buzzword, but you gotta. Here's the science.
I say advocate for your patients, Mark. Okay, but anyway, we're going through the science. Okay, so what do they get? So these are my concerns. There's no healthy muscle profile. There's no controlled virus. There's no dose response. They have this little machine here. They say they're gonna check DUX4. Presumably they did, or this wouldn't be on. They just don't show it, but it would be nice to see that. It would also be nice to see DNA methylation. What you would like to see is DNA methylation goes way up, DUX4 and target genes go way down, and you would like to see healthy muscle, I guess, is 1.6, just like here. That's what it should be if they're saying that they rescued it, not healthy muscle up here like 10.
And this is day 46. I mean, with regular cells and culture, we can't take them out nearly that long. So this was a great opportunity to get that data.
Well, I can't believe they don't have that
data. That is
they
almost 2 months.
They must have that data.
Yeah, it's very valuable data.
So again, we told you it's not all inclusive. I don't know what data they do have or they don't have, but that's the data I would ask for. So I'm not criticizing the data. I'm saying without that data, it is scientifically uninterpretable. that they've rescued muscle
the
function.
data that's being presented here.
And with this experimental design, based on advice from experts in the field, there are questions as if this could actually truly be virus.
Just a virus response.
Getting
Unspecific viral
in.
response.
This is. But anyway, so we don't. So honestly, if we get back to this comment from Dr. Delahorte. Sorry, I don't know how to. I say everyone's name wrong. Is it a rescue of muscle function? I don't know.
No.
So basically, we'd say rescue methylation, doesn't show it. Complete reduction of cell death, not a chance. And rescue of muscle function, uninterpretable.
Yep.
That's our interpretation of the data that they've presented.
Yeah, I agree.
Now, again, if you say that they have other data, that doesn't disqualify this data.
No, we can only judge the data based on what we see.
But if someone says, "Oh, we redid all the experiments, now we have totally different data," that's not valid. That's not valid. Now you can redesign your experiment, do a different experimental design.
But you still have to explain this
data. But you have to explain this data.
Yeah, how did
this data doesn't disappear?
That's right.
So you can't say, "Well, now we've been figured." Now you might say, "Well, we changed the dose, or we changed the card, whatever." Okay. All right, so that's on. So now they're going to do in vivo work, right? And so on xenograft, that's the other way to do it. Look at muscle strength on xenograft. They could actually do ex vivo and actually look at the strength of the muscle, and they can look at gene expression. This is what we do, right?
Yeah, real function.
So what we're doing in xenograft is you're going to grow a human FSHD muscle in a mouse.
Yep.
Okay, and there are a lot of ways to do it. We believe, in our opinion, the way that has been modified by Bob Block at the University of Maryland School of Medicine is the best way.
Yep.
That's our opinion on how we do it. Others can disagree, but there's a reason we think this is the best. Okay, so what Bob does, you're going to irradiate the mouse. That's going to, just the leg though, just the leg, X-ray irradiation. That's going to kill the muscle stem cell.
Right, so the mouse muscles can't grow back.
Can't grow back. Then you're going to injure the mouse with barium chloride. Now, some can use cobra toxin, cardiotoxin, but that's hard to get now.
Yep.
They stopped making it in South Africa. And that's going to eliminate the mouse muscle fibers.
Right, creating a place for your human.
So you basically have no stem cells around to repopulate, and you've cleared out the muscle fibers, but you still have kind of like the egg crate there, kind of some of the extracellular matrix. Then a few days later, you're going to inject human muscle cells, control FSHD, FSHD2, FSHD1, whatever. You're going to inject those cells into the compartment,
right?
Typically the tibialis anterior. And then we're going to stimulate for 4 weeks. We're going to electrostimulate the muscle to get it to grow, get innervated, and get vascularized.
This is the new human muscle cells. You're stimulating them just the way they would be.
So now you have a human muscle
Right.
that is still not that mature, but at least it's an actual muscle
Yeah.
that resembles what you have in your body and what the clinical trial is going to experience.
Yeah. Closest to the patient situation.
It's the close to the patient situation. It's not a completely mature muscle. There's still some immature fibers in there, but it's pretty good.
Pretty good.
Okay, then you're going to, she put, this is actually going to be a retroorbital injection for systemic, systemic treatment of the virus.
Yep.
And then you can evaluate the strength of the mouse. You can evaluate a number of things, and you can take this out as long as the mouse lives. Okay, now one of the caveats, there's no immune system.
Right.
All right, so what is Epicrispr going to do? They're going to do, EPI-321 shows a dose-dependent suppression of DUX4 and DUX4 genes with improvement in FSHD muscle cell survival in humanized mice in 3 genetically different FSHD patients. Okay, so that's kind of odd. So they're going to use the NRG mouse, immune deficient mouse. They are going to irradiate it. Then they are going to hit it with cardiotoxin. So they got a hold of some cardiotoxin. Okay, similar as barium chloride, but then 1 day later they're going to add in the myoblast. So that's quicker than we normally do, but that's fine, whatever. They're going to add in their myoblasts. And then the next day, they're going to add their virus. And then 24 days later, they're going to sacrifice the mouse. So basically, my interpretation of this experimental design is that what they essentially are doing is growing myoblasts in a mouse.
Yep.
They are infecting myoblasts, not muscle. And they are assaying survival of the cells. A lot of cells die, they don't get incorporated now. So they're not doing any electrostimulation. They're not doing any,
This is
they're not doing
basically
force.
a culture dish of human muscle myoblasts
That
in a
happens to
mouse.
be in a mouse.
Yeah, they haven't allowed them to
So this
form
is
fibers.
not the typical way one might use a xenograft model. But that's okay. People do different things. Let's see what they get. I mean, that's not how we would do it. But again, people don't have to do it. We do it. We're just evaluating. I would raise those concerns if I was reviewing the paper, though. I would say that they either have to, let's go back for a second. I would basically say, what are their claims? Improve muscle cell survival. They maybe maybe it does support that claim. It improves muscle cell survival. It is a humanized mouse, so devil's in the details, so anyway.
Well, you want to see the evidence that the
I would just say
xenograft is valid.
I would just say, well, again, it depends on what you're claiming, and I would just make the case that the claims are irrelevant, that the data supports their claims, but who cares about the claims because it's the wrong system. That would be my interpretation, my opinion. Now, other people may think this is really significant. That's fine. People can have it. This is where scientists can disagree. To me, the point of the experiment in a xenograft should be to test your therapeutic in the context of an FSHD muscle as close as you can get to a clinical trial without doing it.
Exactly.
That is the point of doing
Which
it.
that xenograft
And they do not do that.
strategy doesn't do.
But that's not so. But that's fine. But as long as they're not going to claim that.
Okay, well, let's see what the data.
So they're going to say EPI-321 represses DUX4 and improves DUX4 associated phenotypes in humanized mice. Okay. So does the data support the claim? So DUX4 mRNA. Now they're going to look at low, mid, and 3 different doses. And at their highest dose, which we don't know what it is, they might get
a 25% reduction.
They get no reduction with low dose.
No reduction really with mid dose.
10%.
Yeah, 10, 20%.
Maybe if we give them 25%, we'll give them 25% reduction with their high dose of DUX4 mRNA. Again, an idealized situation where you're not actually checking muscle. I mean, that's not disputable. These are not
they haven't had time.
muscles, right? They are infecting myoblasts that are not fused, that are not muscle.
Yeah.
That is just
happened to be in a
how
mouse
it
leg.
is. It happened to be in a mouse leg.
Yeah.
Okay, so that's as long as it's clear that is not an opinion. That is actually what
That's their
what
experimental
they're
design.
That's their experimental design. So DUX4 target gene score, no change on low dose, drops to maybe it goes down 50% on their high dose. Again, don't really know what that is. DUX4 positive human cell nuclei. So oddly enough, now they're saying, this is weird. They must have a hell of a statistician there who's able to figure
These little hourglasses.
if you do enough statistics, you
They
can
look
make
like dreidels,
anything.
don't they?
I honestly, I'm thinking like Dr. Seuss. I'm thinking Whoville. Man. These all look like Dr. Seuss characters. So this is going to be 1. DUX4 protein, oddly enough, goes up in the mid
It
dose.
goes down again.
So oddly enough, DUX4 protein is the highest in the mid dose, where
I'm
DUX4
sure that's not
target genes
significant.
are the lowest.
I don't think any of that is significant.
And nothing significant.
No,
and
0.007,
well,
yeah.
0.05. So,
No,
so in
0.01
the high dose,
They're saying that's significant?
well, it says
Vehicle versus high?
God,
I don't know.
Whatever.
Whatever.
We take their word. We're not going to dispute it. SLC 34A2 protein. That is a DUX4 responsive biomarker. And it goes down with low dose, and again, it's down a little bit in mid dose and a little bit more in high dose, about 50%. And then the tunnel scores, their big thing. They're looking at cell survival. So more cells survive in the high dose. Again, the mid dose gives you a higher, they get this, it's just weird. These dose effects are basically the low dose, mid dose, and high dose don't kind of trend the same.
How do we know that the human cells aren't just dying?
Well, I think that that's what they're assaying. They're just assaying how many cells there are, or something like that. I don't know. Well, it's a tunnel quantification, right? So
well, that is, but just overall, you know, if we
well, that is
believe
what's
these
happening.
different,
We believe that it is likely this is just assaying engraftment.
yeah,
And we know from our own experience that engraftment is highly variable.
highly variable.
In fact, the whole point of doing it the way we do it, 2 points. One is you want to assay as close as you can to a human muscle.
Right.
But two, you just take cells and you inject them. Some grafts turn out great. Some
Some
grafts
are very small, some are
turn
large.
small.
Yeah,
Different cell types have different cultures and different things. So
which is why we need to see the grafts. We
there's
need to
great
see staining for the
variability in the
grafts.
graft, and so you normalize it to the
Yeah.
graft.
You need,
And so
to see
this could
immunofluorescence
be
for the grafts.
conceptually explained by just,
Right, but there's no data
piss poor
here, so
grafting.
we don't know.
we don't actually know.
Yeah,
More uninterpretable data. And again, vehicle control. I don't know vehicles. I like people. I mean, it should be non-targeting guide.
yes.
Virus with non-targeting guide RNA, in my opinion, as a researcher in this space, should be the best control.
Well, DUX4 is a stress response gene, and I know that when you really have to do the right control for these experiments,
Exactly.
because just by infecting cells, FSHD muscle cells, just infecting them with any virus at all, DUX4 goes up. You know, so you really need a proper control, or you're making your job very difficult and your data hard to
Whatever.
interpret.
I would say that I don't dispute their claims, but I'm not convinced by the data.
Yeah.
That's my interpretation. All right, so now we're going to go to wild type biodistribution. So this is actually, I gotta tell you, this just blew my head, man. Blew my head. You're gonna just have it. I gotta tell you, this is, we've been so focused on RH74 and the
Yeah.
virus and focused on methylation, right? Because the virus is delivering the methylation. But there's another key component. And the other key component is going to be the promoter, the gene regulation that tells the CRISPR to be expressed in skeletal muscle. You only want it in skeletal muscle. You only need it in skeletal muscle. And we know that RH74, the virus, is going to go to liver. It's going to go to a ton of different kinds of cells. But the safety checkpoint on that is it's not going to be expressed in those cells because you have a muscle specific promoter.
Yep.
And that's one of the things that Carice made was have a little heart and no heart. We recently published that from our academic lab. Some FSHD optimized muscle specific promoters that are super small and super safe and super effective.
Let's just say there are a lot of them out there. My old mentor, Steve Hauschka, is the king of
you got, 250
the emperor
of them?
of muscle-specific cassettes, and they are being used widely. He's got small ones, ones that are better for heart, ones that are better for skeletal muscle, a whole variety of these things. They are widely disseminated and established.
But
and
a key feature of all of those is what?
Muscle specificity.
Muscle specificity.
Yes, they're
Now
all
you gotta
muscle specific.
See, if you're in my lab, you got to read my mind. Not totally though. That's kind of dangerous. Okay, so let's go to the videotape. Did you ever watch George Michael's Sports Machine? You have no idea, right? Whatever. Before ESPN, highlights Sunday night, Cincinnati, George Michael's Sports Machine. Let's go to the videotape. And he literally had videotape. Okay, so we're gonna now do this is EPI-321 efficacy and safety in wild type mice. So this is gonna now they're actually in a wild type mouse. Wild type meaning it does not have FSHD. It's not just your normal everyday mouse. Okay, so they're gonna look at vector copy number for diploid gene. So they're going to look to see their virus, their cargo. Where is it expressed at 1 month? Where is it expressed 3 months after injection? So where does it actually go to? Sorry, biodistribution. Where does it go to?
Yep, and then
Where is it expressed? Two key things. And I put this little dot here, this little red dot. I say this is TA, tibialis anterior. This is the only skeletal muscle they're looking at. And they're going to look at pancreas, spleen, brain, kidney, tibialis anterior, lung, liver, testes, ovary, and heart. Okay, 1 month. Okay, where does RH74 go? TA is one. Now that's the thing that's kind of striking. TA, they're getting 1 copy per nucleus. 1. Now we don't know what the dose is. Okay, we have no idea what the dose is. But whatever dose they're having, they have 1 copy in each muscle nucleus.
Yep.
Okay. Then they're going to get in the liver, and this is a log scale here, 700, 800 copies per liver cell.
Yep. So remember, this is just a function of the vector. So this is RH74. This is the biodistribution. This is where it gets delivered, in the body.
So 700 times more to the liver than the TA muscle.
Right.
Of course, the liver is a big tissue, and TA is just one muscle.
That's kind of what you would expect.
Okay, with this virus, right? Lung goes to the lung equal, goes to the kidney a little better. Not so much in the brain, close. Actually kind of goes dang near everywhere except the pancreas and the testes. Okay. So in mouse, 1 viral genome per muscle cell and roughly 100 viral genomes. Now I said 100 in the liver because that's at 3 months. In 3 months, the virus is only like at 100 in the liver. Not sure why that is, but anyway, 100 times more. Okay, and that's, they're going to say, is safe. And that's fine. But here's where the rubber meets the road. Transgene expression.
Yep. Look at that. The
TA is going to be...
This should be by far the highest for a muscle-specific promoter.
This is a muscle-specific
You should get far lower expression in non-muscle tissues like lung, liver, testis, ovary, all of those. Now, heart should still be high, of course. Most muscle-specific cassettes should be high in skeletal and cardiac muscle. But these other tissues are far too high, proportionally speaking, for a muscle-specific
So if they're going to call this a muscle-specific promoter, where level, say, 90 in the TA, the level is 100 in the lung. I could call this a lung-specific promoter.
You can't call it specific at all. This is
or liver. You could call this a liver-specific promoter.
We don't know what sequence they're using. We don't know where they got it, but this is not muscle-specific.
How about an ovary-specific promoter?
Activity.
If they're going to say that this shows muscle specificity, are you kidding me?
This is not acceptable for.
And now let's just look at this another thing. Okay, the heart. Right, at 1 month, if you're looking online, at 1 month, copies in the heart, let's say that's 3 copies per cardiac muscles myonucleus, right? 3 copies, we'll say.
Yeah.
What are we looking here? 7,000 level expression level. Okay, so skeletal muscle is 1, heart is 3. That's the number of viruses.
Yeah.
The expression from that 1 in TA is 90, arbitrary, whatever. The expression in heart is like 7,000.
Yeah, which is, remember, heart is not a tissue you need to hit for FSHD.
In fact, we know that high levels of transgene, of any transgene in the heart causes
myocarditis.
Myocarditis.
Not something you want. So this is really,
and then a month later,
it's a little disturbing.
It's just as bad.
Yeah, basically the
same.
So
Dr. Hauschka, the godfather of muscle cell culture and muscle gene regulatory cassettes, if you brought this data to him,
he'd take my PhD away.
He'd take your PhD away.
And rightly so. He would be horrified.
If you said, Steve, I have a muscle-specific promoter. Look.
He has hundreds of true muscle-specific promoters, and they all look a million times better than this.
How did you find the only one that's not muscle-specific in the freezer? I pulled one out of the freezer. I don't know what that is.
I don't know. This is disturbing because we talk about safety, and it's true that this amount of this dose is safe, assuming you're using a muscle-specific promoter, because everybody does. Everybody in these trials, everybody in these mouse and dog, all the preclinical experiments for any disease in muscle gene therapy uses a muscle-specific creatine kinase, muscle-specific promoter. And
now we're not saying this isn't safe.
but look at this transgene expression. This is transgene expression you would normally never see in these non-muscle tissues.
You would never,
So
for
is this
anything.
safe?
Well, no, wait a minute. They say it demonstrates safety. They say they didn't see any pathology. That's fine. I'm not worried about. You got to remember, this is 1 month and 3 months in a mouse, right? So my concerns are muscle-specific promoter. Just shocking that anyone would call this. I don't know what it is. It's probably free, like RH74 was free. Meaning no licensing fee.
I would still want to see longer than 3 months.
So no, just hold on. So
for safety.
But that's the key. We're talking safety is being two things. I don't even want to say safety. We're not saying this isn't safe. But what happens when it's expressed in these tissues? You start to trigger an immune response.
That's what I'm saying.
And the immune response can lead to clearance of cells.
Yeah.
And over time, you could have chronic issues that might come up later than 3 months conceptually.
Yeah, which people have seen in animal models.
In fact,
especially with CAS.
if you had listened to one of the previous podcasts, I'm sure you were glued to it and late at night, as you probably are, before dozing off, listening to the podcast. You would have heard that the suggestions from the real powerhouses in gene therapy, when they said, what have they learned from all these trials? And one of the things was the improved safety is to truly have a muscle-specific gene regulation to go along with a myotropic AAV.
Yeah, people have known that for decades.
So people are trying there's all these things, technology, to not get expression in all these tissues.
Yeah. Now this takes us back
and
like
here
50
we're
years.
looking at all this. You basically say, oh, gene therapy in 1980, right? I mean,
no, there's no reason for this
that we can think of. Again, this is our interpretation. I look at now someone else. Now that's fine. I would love to have someone else let me know how they look at this and explain to me how this. Again, you're looking at comparable levels of virus, except for the liver. Comparable levels of virus. Comparable levels of gene expression in non-skeletal muscle tissue, and astronomical levels in the heart with comparable levels of virus. Again, heart's a muscle, so I guess you can give them a pass on that, except that you don't want it that way in FSHD, and you don't need it in FSHD, and you don't want it because of myocarditis. In fact, that's one of the whole reasons people are so excited about your cassettes that dial down the level in the heart so far, because in fact, like universal excitement over, they didn't care about FSHD, that dialing it down in the heart would be so much safer and better.
For a lot of these other things.
But I don't see, I would love to hear another explanation that this is a muscle-specific gene regulation. And while it may be safe in a 3-month trial in the mice, one could conceive there could be concerns.
Yeah, up to 6 months or even later.
Or whether it's safety, but even concerns potentially about also just efficacy.
Yeah, exactly.
You're basically loading up the lung, the heart. It's just, anyway. It is strikingly unusual.
Yep. You don't want antigen presenting cells to.
Okay, so the conclusion is the Epic Bio. Well, now this is Epic, so actually, whatever. Must have been an old thing.
Yeah.
Identify highly effective modulator combination suitable for treating. I agree. I still think the platform is fine. I'm not knocking the platform. I'm not knocking the company actually
Just
at all.
experimental design.
Hyper compact dead cast, great. No problem with that I'm aware of yet. Represses DUX4 downstream pathways. In their version of a humanized mouse model, fine. I do not think that's a relevant model. In my opinion, that's not a relevant model. Improves survival in vivo, who cares? But I guess supports that. Whatever, who cares? Demonstrates a safety profile in preclinical studies, indicating the readiness for first-in-human studies. I would just disagree with that. I would disagree. I would not take this to clinic with this. I would change the capsid. I would change the promoter.
Yep.
And
myotropic, next generation capsid, and definitely a better real muscle specific promoter.
And at some point, some experiment along the line. I would test to see if this actually works in the target tissue or the target cell.
Yep. And I would want a dose that we know is going to be safe and efficacious in vivo.
Okay, so those are things that we would do. Everybody
else we know,
but again,
in the gene therapy field.
Everyone else in the gene therapy field might, I mean, but again, this is what we would, this is, you know, we always got to be careful when you look at someone's grant to not write the grant form. What you really should do is this, you know, you can just basically say, this is not going to answer the question. And I think what you're getting at is the gene therapy field has answered a lot of these questions.
Yeah.
You don't have to take their advice, but the grant's not getting funded.
Yeah.
The paper's not getting published. And the grad students fail in their qualifying exam if this is the data.
Yeah.
In my opinion, if I'm on the committee, which is also why I'm not on any grad student committees, actually, because I believe you have to earn your PhD. You don't just get given a PhD. And so students don't put me on their committees anymore.
Very wise of them.
If students were any good, they'd have me on the committee. And actually, I have been on some good student committees in
I've
the
always
past.
appreciated having tough people on my committees because
Good
they
students
give you
have
great ideas.
good students
I want for the
always
toughest
want the
people on my
toughest committee.
committee.
That's because
I
you're
had
brilliant.
Richard Palmeter and David Kilman, Edith Long, you know, from Bob Pugin's lab. I mean, they were tough. They gave me
Oh,
great.
hell, I
they
had
gave me
Danny
great
Reines,
advice.
Jerry. Yeah, I had a really ballbuster committee. No,
But that's what you
the
want.
good students have tough committees. Loser students have easy committees. It's funny. Everyone always ends up on the same committees. Yeah.
Yeah.
I'm not on any student committees, and now you guys can see why. This is how I treat you. But if your goal is to be a good scientist and to have good data and to actually deserve your PhD, which is unfortunately not the goal of students these days, you might want us on your committee. All right, so we got one more piece of data to go over. I know we've been going a long time. Sorry, folks. Non-human primate safety study of high-dose EPI-321, a novel AAV-delivered epigenetic editing gene therapy for the treatment of FSHD. Okay, this is the primate data. We've looked at mouse data, wild-type mouse data, and we looked at some xenograft data. This is now in non-human primates. All right, let's see what they got. So they're going to do basically groups of 4, 2 males and 2 females. Cool, fine with that. They're going to do 1.2 times 10 to the 14th vector genomes per kg. Okay. Doesn't really matter how they do the math on it because in the end, this is the math they're going to use for the clinical trial. So they actually state that this is going to be 6 times higher than the clinical trial dose. And so that's 2 times 10 to the 13th is the clinical trial dose.
Right.
Okay. So they're going to have groups. They're going to do EPI-321 by itself. They're going to do EPI-321 plus prednisone, and EPI-321 with a triple immunosuppression of prednisone, sirolimus, and rituximab. So they're going to wipe out your inflammation and your cellular immunity response. Okay. All right. So this is how they're going to do the dosing, right? So now one thing that they note here in the very beginning. It says high dose AAV is required for effective muscle delivery. They know this. Everybody knows this.
Yeah.
Class effects of AAV vectors in non-human primates include early immune-related toxicity, such as complement activation, thrombocytopenia, and elevated liver enzymes within the first week of dosing, occasionally necessitating unscheduled necropsy. Okay, so they're going to address everybody in a Duchenne trial is getting prednisone, for example. So you get immune suppression. They're going to do rituximab, sirolimus, and prednisone. So what are they going to do? So the rituximab treatment, that's going to eliminate your B cells, so you cannot make antibodies, and it's going to take you like 6 months to recover. You being if you were a monkey, but also you as you, if you were getting this treatment. So they're going to wipe out the B cells. Sirolimus is rapamycin, mTOR inhibitor. That's going to prevent proliferation of any B cells that don't get wiped out, but also proliferation of your T cells. Your T cells can't ramp up. So that's an immunosuppression, and that takes you 60 hours to recover for your T cells to come back. But essentially, they're going to wipe out, so for the first 2 weeks, they're going to wipe out your B cells and your T cells, okay? And the corticosteroid, right, anti-inflammation for 3 weeks, and it can take you up to a year to recover. So they're going to do a prednisone alone, and then a triple, and they're going to look to see what's going on. right? And they said all animals survived, no clinical findings, so everything's cool. And really just nothing no surprises. So general safety transport, they say prednisone alone was as safe as a triple immunosuppression. And they're going to look at total of 39 total days after, I believe is that 39 days? 39 days after administration of EPI-321. Okay. So we're talking about safety again, in a very limited 39 days, it's safe. And let's look at that. That means that, well, your prednisone is still functioning even though you're not on it. You're still getting your anti-inflammatory effect during this time. So we don't know what happens after the anti-inflammatory wears off. And you might start to get your T cells back, but you're not going to have any B cells. Okay.
Okay.
So, whatever. But their point is that if you don't touch the B cells and the T cells, it's equally safe. Okay. Cool. All right, now they're going to go through and they're going to look at some of the cells that are there. They're going to look at natural killer cells, natural killer T cells, monocytes, and dendritic cells. These are antigen-presenting cells. And they're really only going to look out to 8 days post-dosing for reasons, even though they went out to 40 days. So it's interesting. Blood work probably is each one of these red marks. And it looks like they have day 15, day 22, day 39, and 3 in between day 22 and day 39. We're not going to see any data on that. So they have the data. I'm sure the FDA saw the data. Other people saw data, but we're not going to get to see any data. So all we can do is evaluate the immune response 8 days while under massive immunosuppression. And what they find is EPI-321 alone stimulating an NK proliferation. Natural killer cells are going up, so triggers an immune response.
Yeah, not too surprising.
You can suppress that with the prednisone or the triple immunosuppression. Okay. Now they're going to go and they're going to look at transgene copy number in skeletal muscles and transgene expression in skeletal muscles. And keeping in mind, this is 6 times higher than they're using on people in clinic. And the point of this is safety. However, I want to look at this in respect to durability and efficacy. Okay?
Yep.
So, remember, this is 6 times higher than what they're going to use in clinic. Right? And the clinical trial only is going to have prednisone. So we care about the blue one here. If you're not looking online, we care about the blue one with the red dot. Right? This is the one that's most relevant to patients.
Yeah.
All right, let's look at transgene biodistribution. So what they're going to say is immunosuppression potentially enhanced biodistribution. Okay? And so we're looking at the figure on the left, and we're going to focus on the dose. Okay? At 1.2 times e to the 14 in monkeys, they are going to get, in the prednisone, right, I'm going to give them 120 copies per nanogram. Okay? 1 nanogram of DNA equals 152 cells in human. So we're going to say primate's probably the same, non-human primate, close. So that means 120 copies per, so less than 1 copy per cell. Okay?
Yep.
Less than 1 copy per cell at 6 times more. Now remember, you need 12 copies per cell in an ideal situation to get a 40% reduction of DUX4. They're doing this dose 6 times higher, and they're getting less than 1 copy per cell, right?
Yep.
Okay. Clinical trials prednisone. Okay. Do all the math. So if you calculate it out, at a dose of 2 times 10 to the 13th viral genomes per kilogram, we would estimate they're going to have about 1 about every 8 cells. And at the high dose, about 1 every 4 cells with prednisone. Now, the interesting thing is, without prednisone and without the triple immune suppression, the numbers are much worse, which tells you that the immune system doesn't like this.
Yeah.
Okay, so clinical trial will have 1/6 and 1/3 the dose of AAV. And again, you need to have 12 copies per cell to get 40% repression and 8.5% methylation. And we're at fractions of copies per cell.
Yep.
Okay. So let's just jump to the dog data really quick. I'm going to go back now to some dog data and say, okay, remember in the dog, what we saw was at 1 × 10⁻³, right, where we're basically at where if you're around 1 vector genome per nucleus, I saw 5% positive fibers, no dystrophin based on Western, 5% positive fibers at about the levels that we're talking about here, right?
Yep.
Right, at the high dose where you had 7 vector genomes, so you had to get the 7 vector genomes. Now the thing that's really strange, right, if you think about this, they're at 2 × 10⁻⁴, right, and their dose is really, I mean, they're getting so little. This is really getting cleared.
Yeah.
I imagine that's what
I think so. Yeah.
Okay. So let's just look at this for a second. It's 6 times the initial clinical dose, right? 1.2 × 10⁻⁴. They're at less than 1 cell per nucleus.
Right.
On their thing, right? 1 copy. The dog with dystrophin was at 7. So they're already way below. So now we're doing these comparisons with the dystrophin trials. So at a higher dose, 0.2, right, at a higher dose than the dystrophin, they're getting much lower efficiency. Okay. So looking at the dog data and the mouse data from other things, those are still like, you're going to be lower than that. So at a dose of 2 × 10⁻⁻⁵, right, you're really, on their data, it's really low. So let's look at their clinical trial. EPI-321, 2 × 10⁻⁻⁵, you're basically, based on their data, their own non-human primate data, they have 1 per 8 myonuclei or 1 per 4 myonuclei. That's what their data says. And you need to have 12 per cell. So instead of 1 per 4, you need 12 per 1.
Yep.
50 times more to get the 40% reduction in DUX4 based on their data.
Yeah.
Okay.
Yeah.
Not my data. That's my interpretation of their data. All right, so let's look at now expression. Now that, remember, we told you now that's biodistribution. So let's look at transcript. So it's really interesting. You're getting virus in the prednisone treatment.
Stuck
somewhere because they're not expressing the transcript. Right? Now we're looking at transcript copy number. Again, now this data is all on day 39. So this is day 39, right? And if you're looking online, what you're going to see is that the expression of the cargo with prednisone or no prednisone is the same. But with the triple immune suppression, it's like 6 times higher, right? It goes from 50 to 300. So this suggests that, now they're going to say that it enhances biodistribution. I'm going to suggest that by eliminating the B cells, the body can't make antibodies against this. Okay. And I'm going to suggest that by eliminating the T cells, you're eliminating the cytotoxic response, that what's really going on is the cells that express the Cas onyx are getting cleared in the prednisone and in the no immune suppression, and they're not being cleared here. Okay, in the triple suppression.
Yeah.
That's my interpretation. Okay. So that's when, now, the key is, in the clinical trial, you're not having triple immunosuppression, you're only having the single dose. And even if you were getting triple immunosuppression, it's going to wear off eventually. So this suggests to me, now you could state that a different way and say you have better biodistribution by immunosuppression. I say it's the distribution's the same. It's you maintain the cells that have,
Yeah.
But again, that's my interpretation.
And this is all in muscle, right?
This is all skeletal muscle. They're only looking at skeletal muscle.
So that you think the reason they still get the biodistribution as good as it is things are just kind of getting, these cells obviously aren't getting cleared, right?
Well, these aren't
Those
expressing.
even cells, yeah.
Well,
just
we
not
know these
expressing.
aren't expressing. So,
Yeah.
so sorry. If we go back, you look to the left, right? It says that the blue one here, where the transgene copy number is like 110,
Yeah.
but the expression level is you're getting twice as much transgene copy number in the prednisone versus no prednisone, but equal expression level.
Yeah.
Just tells you that a lot of the cells here are not being, so basically a lot of
I
stuff
wonder
is.
if the not muscle specific promoter is getting shut down too over time.
We don't know that's a short time, but yeah, it's possible.
Yeah.
But it's not getting shut down in the triple.
Right.
So
No, I'm sure there's clearance of the Cas expressing
I mean,
cells too.
that would be my interpretation because. So remember this paper?
Oh, yeah.
You showed me this paper.
Yeah. That's a great paper.
Dongcheng Duan, Cas9 specific immune responses compromised local and systemic AAV CRISPR therapy in multiple dystrophic canine models from Nature Communications 2021.
4 years ago.
Right? Treatment results initially in robust cargo expression in affected dogs, but also induces muscle inflammation and Cas9 specific humoral and cytotoxic T lymphocyte responses that are not prevented by the muscle specific promoter and transient prednisone immunosuppression. So even if you have a muscle specific promoter, you get clearance.
Right.
But the reason you want the muscle specific promoter is to prevent the immune response. And we already saw that they don't have a muscle specific promoter in our opinion.
Yes.
So they go on to say, our results suggest Cas9 immunity may represent a critical barrier for AAV CRISPR therapy in large mammals. And without going through all the data again, the point I want to make is that with only prednisone treatment, within 3 weeks, they are getting an immune response in dogs against Cas9, a T cell response, cytotoxic T cell response. Granzyme B is killing the cells, the natural killer cells. That basically what is going on within 3 weeks, really going at 6 weeks, and by 12 weeks, what's going on at 12 weeks is virtually all, look over here on the right panel if you're looking online, at 3 weeks, you get a few Cas9 expressing cells. By 12 weeks, they're almost all gone. They've been cleared by the immune system at 12 weeks. At 6 weeks, right, you have some expressing and some not expressing. We just know by 12 weeks.
Yep.
So,
and this is for dogs.
So 6 times 7 is 42 days. The Epicrispr was 39 days. So they are not even looking at 6 weeks.
Right.
So this data says at 6 weeks, you're really starting to lose it.
12 weeks, it's gone.
Gone.
All the cells have been cleared.
Okay, and it's a reaction to the Cas9.
Yep.
And the reaction to the Cas9 is through a T cell mediated response, right, which they are eliminating in their triple immune suppression.
Yep.
And so
that's why you still see expression with the triple IS.
In my opinion, in my interpretation of the data, it looks to me like they are getting a response. The data supports, in my opinion, a response to Cas9 expressing cells and leading to a clearance of Cas9 expressing cells by the cellular immune response, adaptive immune response.
Right.
So even if you fix everything with delivery,
there's still this problem for
what's going to happen in a few weeks,
and this is something we all have to deal with.
There will be no Cas9 expressing cells, meaning, and the cell, it's not that they're getting rid of Cas9, remember, they're getting rid of Cas9 expressing cells.
That's right.
So if you methylate the DUX4 gene in cell A, and you do not methylate the DUX4 gene in cell B, because cell A has Cas9 and cell B does not have Cas9.
Right. You fix a cell and then it gets destroyed.
So cell A gets eliminated, you're only left with B.
It doesn't do any good.
That's not fixed.
No.
So it's not like you're fixing it and then those are being maintained.
Right.
Because they're not replicating.
No, the cells that you're fixing are getting eliminated. That's
so
the
that's a
problem.
concern. Now, this is what the data says to me.
Yeah.
That's my interpretation. I would welcome someone else explaining to me how this data does not support that, or that you can't conclude. I mean, obviously, histology would be nice to see. We'd love to see some histology. We'd love to see this at 12 weeks. I'd love to see some antibodies, some serum, Cas9 stuff. And they may have all of that
some
data.
spot assays, some
Right, I'm sure, and if they have all the data that says, hey, this thing sticks around forever, I hope they do have that data.
That would fly in the face of everything we know that's been published.
But this data
Cas immunity.
and the dog data and the other data, granted it's a different Cas protein, but everything suggests there's going to be a durability problem.
Yeah.
In fact, the take-home message in dogs using DMD dog models and other Cas9 proteins that we show that strategies commonly used to minimize cellular immune responses like tissue-specific promoter, prednisone immune suppression are insufficient to bypass Cas9 immunity. Comprehensive approaches, including but not limited to the use of immune-attenuated, immune-privileged Cas9 gene expression cassette, non-viral vector-mediated transient Cas9 gene expression, immune tolerance induction, more potent immune suppression, and pre-screening for Cas9 immunity might be necessary to translate AAV CRISPR therapy to DMD patients.
Yep.
Now that's DMD, and there are a lot of differences, but let's put it all together, okay? Let's put it all together, okay? If I'm reviewing this paper, if I'm examining the student presenting this data, if this grant came to me for, and again, I was chair of the Skeletal Muscle and Exercise Physiology Review Panel for NIH for 2 years. I've reviewed a few grants. I've reviewed God knows how many papers. A lot of people don't like to send their papers to me. I think I'm an excluded reviewer now.
I get them instead, which is not fun.
I recommend it. They haven't learned to exclude you too. Well, because you only want, again, you're not picking at people. You're saying, is this science? Good.
Yeah, no, the best paper to review is one that doesn't have any problems. Like,
I
this
know.
is great,
If you're,
it's fast, it's easy. You can
I
just,
know.
Actually,
when
things are great. They're great for the same reasons.
When I read a grant, bad grants, it takes you forever. It's like, oh my God, it's painful. Oh my. But really good ones. All of a sudden you're through it. You're like, holy crap, that's exciting,
really
interesting, really good.
Yeah.
And so it took me 3 months to put this podcast together.
I know, many trial runs.
So anyway, concern one, big concern. The dose may be safe, but I'm concerned they will have little, if any, chance of being efficacious.
Yeah.
So I didn't see any efficacy data for deciding that this is the dose to use. There must be some data. I don't know how this was chosen, but I've seen no evidence. Were any relevant in vivo efficacy experiments? I have not seen any experiment that, in my mind, for my criteria, are relevant.
Yep.
Other people have different criteria, that's fine. What is the biodistribution for the clinical trial dosing in a large animal model? I would like to see what they did with the mouse.
That would be useful for all of us to know.
But it'd be interesting in the mouse.
Yeah.
They showed the mouse and they said, here's the distribution. We don't know what dose that was, but they
in
said
a primate, that would be
in a primate, not just with their 1.6, and they must have that data. They probably dissected out all the primates.
Yeah,
but I want to know
trial dosing.
on their clinical trial dose, what is the biodistribution in the large animal?
Yeah, that'd be good.
And I'd also like to know in the non-human primate the level of expression with only prednisone treatment. And again, with
mimicking the trial as much as possible.
But not just looking at skeletal muscle,
Right.
but looking at all the muscle.
Yeah.
Now, granted, this is I'm sure they have that data, so hopefully that supports everything. Concern two: the benefit, if any, will not be durable due to clearance of cells expressing the Cas.
Yeah, that is a big thing, and it's a problem for all of us working on Cas-mediated gene therapies.
No, absolutely.
Yeah.
In fact, and it's been around, but people have known about it.
That's right. This is not a new thing.
For 4 years.
Yeah, Dongsheng's paper is 4 years old.
That's right.
So we all had time to prepare.
I mean,
for
if you
this.
think about it, right? Muscle-specific cassettes, truly muscle-specific cassettes, have been
those
around
have been around way longer.
since the 80s, right?
Well, yeah.
Next generation myotropic AAVs have been around. I mean, Solid Bioscience already has clinical data on Duchenne, so you can get one of those.
Half a dozen of those around,
Right,
and all being used. Yeah.
So this is a question. It would take 12 weeks to answer this question.
Right.
In a wild type, just a non-human primate, a dog, or a pig. Just answer, not a mouse. Mouse is not the right experiment to do, even though mouse does have some durability. The proper, right, answer the expression. Will the expression of Cas onyx protein be durable?
Yes.
What happens to the cells expressing this?
Yeah.
Because if they get eliminated,
There
the
goes your
therapy doesn't work.
It's
There's no
over.
therapy.
It's done,
You're done.
And you can't re-administer. That's
Okay.
it.
Question, is this a muscle-specific promoter? Because it doesn't
Really
look like
doesn't
it.
look like one.
So doesn't the fact that it expresses in all these other lead to this first problem?
Yeah.
What about immune cell activation up to day 8? Whatever, they didn't want to show it. Will there be an adaptive immune response
Right.
after immunosuppression
Right.
wears off?
You
Again,
wanna see
that's
that.
you're not going to be on immunosuppression forever.
Yeah.
What happens afterwards? Because
Yeah.
again, you can answer. You don't have to take
How
years to
durable will
answer
this
this.
be?
Yeah.
Yeah.
Are there antibodies developed against Cas9 when only prednisone was used?
Right.
This should be known.
That's an easy question to answer.
And again, they may have that data. I don't know if they'd have the data or not,
Yeah.
but I would want to know that.
Yeah.
I'd ask for that if I was reviewing the paper.
Absolutely.
And the biodistribution in the IIIS supports that AAV-infected cells are being cleared in the MPSS alone. I would like them to show that that is not the case.
Yeah.
Because the expression is the same as no prednisone, and we know from the dog data, so those are my concerns.
Yep. I think that's fair.
All right, now we're finally, after 2 hours, we're going to our song.
If everyone's still awake. Song will wake them up.
Vidalia's Faking It. You a big fan of rockabilly?
Oh, yeah. Yeah.
I love it. And I gotta tell you, I was in Atlanta for grad school at Emory
Oh,
University.
here comes the Southern. Just wait for it, people.
Used to love to go to the Star Bar in Little 5 Points. And still there, actually. I was there
nice.
for a reunion, and it's still there. I didn't go in after a 56-year-old popping into a rockabilly
younger
sort
venue.
of punky sort of thing. But I love it. So I got this CD. You know what a CD is?
Yeah, I'm almost as old as you.
I got this CD from the Bubba Palooza.
Wow.
Right? So they used to back in the day. It'd be, when the band takes a break, they sell merch,
Yep.
and you can go buy a
I've heard
CD
tell.
for $20. And I got Bubba Palooza, because it was 1995, Bubba Palooza, great. Some of my favorite bands. You got Redneck Grease Deluxe. That's my favorite song is, Mama Was a Dancer at the Claremont Lounge.
Yeah. You've sung it many times.
I love that song. A great song. Don't You Touch Her. And then, but you had Southern Culture on the Skids, Deacon Lunchbox, just some really great local band, great music scene. But anyway, the Vidalias and Faking It. All right. For no particular
reason.
Not see through. Well, I was kind of disillusioned when it finally hit. You really ain't so great, you're just faking it. chance to contradict the thing I say. You bend my ear for hours on end, complaining how you feel, and you tell your therapist that I'm a heel. Well, something should have told me you were too good to be true, but you put on a happy face, but I could not see through. Well, I was kind of disillusioned when it finally hit. You really ain't so great, you're just faking it. You really ain't so great, you're just faking it.
All right. So only one song for the 3 podcasts. It's really one big giant podcast, but Faking It by the Vidalias. I love me my rockabilly. And always fun, good music down there. Not too serious. Anyway, so, just to summarize up the preclinical data, honestly, it's just, I'm shocked at some of it, disappointed in others. Say what you think. I mean, I had high hopes for this, honestly. We believe in CRISPR inhibition. I thought, boy, maybe they have solved some problems that we hadn't solved. Because we did actually our first, honestly, the first thing we tried back in 2014, in 2013, was to try to remethylate, bring in DNA methyltransferases. And the truth of the matter is, for fully differentiated non-replicating cells, we couldn't get them methylated. And the more we thought about it, the more we thought, well, would methylation even do anything? Because you really need to flip this entire epigenetic switch. And that's when we decided, it's actually, while lack of methylation is a striking feature of FSHD, it's not clear that restoring methylation in differentiated skeletal muscle is the answer. There's epigenetic repression may or may not be the answer. I think it would be if you could get it, but do you even need it? Because the cells aren't replicating. Again, epigenetics is about heritability. What you really need is just to shut the locus off. And that's actually what my research lab has decided to do. That's why we use a different type of CRISPR inhibition. We're just going to drop a big old off switch there. But again, Epicrispr chose a different approach, methylating the region, and we know others are trying that approach. But we went through the data, and I got to tell you, I didn't see a single thing that told me they were actually methylating a differentiated FSHD locus, turning off DUX4, losing target gene expression. And then when you get to issues such as durability, which is a huge concern. I got to tell you, we weren't thinking about that originally. Everyone's like, oh, these are foreign proteins. You got to watch out. You're expressing foreign proteins. You think, muscle's not that big of a expression cell, antigen presenting cell. And we know that dystrophin's a foreign protein for Duchenne patients, right? Because they don't have dystrophin, so actually adding it should be, in that stage, that's fine. We thought, okay, maybe it'd be okay. Of course, now after Dongxing Guan's paper came out, and we saw that the Cas proteins are, in fact, cells expressing those are eliminated, and the data presented, while not conclusive, points in that direction, that cells are being eliminated. And the experiment was not done long enough to actually show you. But boy, everything is trending in the direction to say that there's going to be durability concerns. I end up with three big concerns. One, I'm not a fan of RH74 as a virus. I don't think that you can put enough of that into a person safely with any cargo for FSHD, number one. Number two, I've never seen any promoter, DNA regulatory element, like the one shown in their preclinical data, that is called muscle specific or specific. Honestly, it looks like CMV. It looks like just a promoter that expresses everywhere. That's what it looks like to me. Sure doesn't look muscle specific. Their data does not show. They might come back and say, hey, we're using whatever, CK, we're using what. Then if the answer is that they're using a well-documented, well-known muscle specific promoter, then they don't know how to do science because their science doesn't show it. Okay, you lose either way, okay, in which case you can't trust any of the data. So if you trust that they can actually do the analysis correctly, it's not a muscle-specific promoter in their context, whatever they did to it. So the virus has got concerns, the promoter I've got concerns, And then the whole fundamental mechanism of action. We had concerns even beforehand. Can you actually really change all the epigenetic? Again, it's not about DNA methylation. That's just one component. You can point to my old papers, my 98 paper, where we show that DNA methylation has methyl binding proteins come in, and then you can actually set up heterochromatin in replicating cells. Okay, replicating cells. And actually, it turns out that's not typically the way it actually works. That turns out to be a rare, so yeah, there's methyl binding proteins, but the reality is that the methylation machinery that puts the methylation on, yeah, you have methyl binding proteins that come in, but you also have all these, like heterochromatin protein 1, for example, comes in, and you modify the histones, and you modify the whole region, right? And that's how you establish repression. And it all happens, as far as we know, in S phase, replicating phase, not in G0, okay, in these cells. And no one that I'm aware of has ever shown this in any cell type that's not replicating. You can just you may be able to add a methyl group, but can you actually change the epigenetic state? So another question might be, well, how do you get repression? Didn't they show some repression? Well, again, it's not clear. It sure looks like the cells that they're working on are replicating, which is going to change the situation. But let's say they're not. Let's say they hit the target tissue. Not knowing where the guy, it's quite possible having CRISPR interference. But the DNA methyltransferases themselves are transcriptional repressors. For all we know, it's just sitting there and repressing as it should, which actually would be fine. But then it's a different mechanism of action. And maybe that's what it's doing. Maybe it's just sitting there as a repressor. Now the repressive domains of the DNA methyltransferases are not the same as the methyltransferase domain, and we don't actually know what domains are there, or if this actually functions as a transcriptional repressor. Really, we don't know what the components are in here, so we can hypothesize that could be the case. Either way, I think there's a lot of questions. Is it working, and how is it working if it is working? And will this persist? But more importantly, durability. Huge question about durability. Is it going to stick around? So I guess that's 4 things. That's 4 things that I have major questions about before I would go to clinic. I want answers to all 4 of those things. Okay, well, I would want a better viral capsid. I'd want a proper muscle-specific promoter. I'd want to know for sure that my cargo works in the target tissue. And I'd want to know that the cargo expression, the cells expressing that, stay around for a long time. All that should be known before going to a clinical trial. But that's me. That is my opinion. That is how we do things. I was taught in grad school by one of my advisors, Dr. Linda Gooding, you can't force people to do science the way you would do science. Take care of yourself, worry about yourself, which is fine. But you know what? I also worry about y'all. And someone's got to advocate for you. Doesn't appear anyone's gonna. So here we are. So we'll take the heat. Anyway, come back for part 3 and we'll go over the clinical trial.
Thank you for listening to the MyFSHD podcast, where we share with you the latest news and information on FSHD as we strive for a cure. Do you have a question for Peter? He'd love to hear from you. You can reach him at peterjones@med.unr.edu. Thank you for listening, and join us again next time for more news and information.